Welcome to Submodule 1 of 4 on drilling mechanics, shock and vibration, which are critical factors influencing performance and equipment reliability. In this session, we'll explore why shocks occur, how they impact the drill string and bit, and the practices used to minimize them for optimal drilling efficiency. In this submodule, our learning will center on 5 main objectives. First, we will explain why shocks must be monitored during drilling operations, both from an energy efficiency perspective and to protect equipment. Second, we will highlight the relationship between shocks and drill string damage, showing how even minor impacts can shorten the useful life of tools. Third, we will review good drilling practices and demonstrate how applying them directly translates into operational savings. Finally, we will examine the major contributors to rough drilling, including formation properties, borehole condition, well path, and hole cleaning efficiency. Together, these objectives will give us a comprehensive understanding of shock and vibration control in drilling mechanics. With that roadmap in mind, let's begin by looking at why shocks matter in day-to-day drilling. Shocks are important to monitor because they directly impact drilling efficiency. When we rotate the drill string, energy is delivered to the bit in 2 primary forms: rotation, measured as revolutions per minute, and downward force, measured as weight on bit. Ideally, this energy should all go into breaking the rock and deepening the wellbore. However, when shocks occur, a portion of that energy is wasted as vibration rather than rock cutting. In other words, the energy used to create a shock is energy lost from the drilling process. This loss doesn't just affect the immediate drilling rate. Over time, high shock levels increase wear on the bit and bottom hole assembly, leading to reduced performance and premature tool replacement. By minimizing shocks, we maximize the efficiency of energy transfer, which in turn improves rate of penetration and extends equipment life. So, the key message is that every uncontrolled shock event represents both wasted energy and additional cost. With this principle understood, we can now move to the second perspective: how shocks directly damage drill string components. Shocks are not just an energy efficiency problem. They also have a lasting impact on drill string components. Every tool in the string, from the bit to the surface connections, experiences stress when shocks occur. Even if the component does not fail outright, repeated shock exposure weakens its structure over time. This progressive damage can reduce the effective lifespan of tools and assemblies. For example, connections may suffer micro-cracking, stabilizers may wear unevenly, and sensitive tools such as measurement while drilling or logging while drilling equipment can lose calibration accuracy. The end result is higher maintenance costs, shorter service intervals, and a greater risk of unexpected failure. For this reason, shock history must be considered during inspection and servicing. Equipment that has been exposed to repeated shocks may appear functional, but without accounting for its shock loading record, we risk redeploying compromised tools. Ultimately, monitoring shocks is a proactive way of protecting both performance and reliability. By understanding the cumulative impact of shock damage, we can plan maintenance more effectively and avoid costly downtime. Next, let's connect this to how good drilling practices translate directly into measurable savings. Good drilling practice is more than a procedural guideline. It is a driver of cost savings. Research presented at the SPE conference in 1996 by Mason and colleagues demonstrated clear evidence that minimizing shocks directly reduces operational costs with a 33-day saving per well compared to offset. The logic is straightforward. Fewer shocks mean less wasted energy, reduced equipment wear, and a lower likelihood of tool failure. In practical terms, this translates into fewer tripping operations to replace damaged components, longer bit runs, and reduced non-productive time. It also decreases the frequency and severity of inspection and repair cycles, which lowers overall service costs. Most importantly, it improves drilling consistency, which allows better forecasting of time and cost. So, the message here is that good drilling practice is not only about maintaining safety and technical standards, it directly improves return on investment. By embedding shock reduction into everyday operational practices, operators achieve a measurable bottom line benefit. With that in mind, let's now explore what actually contributes to rough drilling, since understanding the causes of shock events is the foundation for preventing them. Rough drilling arises from multiple interacting factors, each of which can trigger or amplify shock and vibration. Let's work through them. First, formation effects play a significant role. The coefficient of friction describes how easily the drill string moves along the borehole wall, while the coefficient of restitution represents how much energy is reflected back during impact. Both values depend on rock type and directly influence shock severity. Second, hole gauge and shape are critical. We plan drilling for an in-gauge hole, but in reality, caliper measurements later often reveal washouts, ledges, or under-gauge sections. Any deviation from true gauge increases the chance of vibration as the drill string contacts uneven surfaces. Third, the well path itself affects dynamic loading. High dogleg severity or sharp curvature creates elevated side loads, increasing friction between the string and the borehole. Finally, hole cleaning plays a vital role. Poor cuttings removal allows debris to bind the drill string, causing stick slip and torsional vibrations. Taken together, these factors explain why drilling mechanics are complex. Rough drilling is rarely caused by a single variable. By analyzing and managing these contributors, we can reduce shock events and improve performance. Next, we'll use a video example to illustrate shock and vibration in action.
As you know, both shock and vibration are prime culprits in many drilling problems. Today we are going to discuss how to minimize their effects and thereby improve drilling performance. Shock in a drilling environment is the sudden input of energy from impacts of the bit, BHA or drill pipe with the wellbore. Vibrations can result from the shocks. Rapid and continuous vibrations result in fatiguing of the drill string connections to the point of twisting off. This is why many drill string failures are the result of cumulative fatigue due to vibration and have regular inspection periods. Shocks are measured in G's by an accelerometer. 1 G equals the force of gravity. Shock magnitudes registered via downhole tools can exceed 200 G's. The severity of the shock depends on 3 parameters. 1. The magnitude of the shock. 2. The duration or length of time of the shock. And 3. The frequency or number of shocks. Magnitude is the force the tool sees when it impacts the borehole wall. Duration measures how long the shock lasts in seconds. Frequency is the number of times the tool sees a shock greater than the accelerometer's threshold. Shock and vibration and poor drilling mechanics can adversely affect ROP, slowing the drilling process. So how do we detect potentially harmful shock and vibration? Surface and downhole data in both depth and time formats are used to diagnose downhole conditions. Looking at the drill string and bit after the run will also help to determine the severity and type of shock and vibration. Schlumberger measures lateral shocks in all of their tools. These tools have shock sensors that measure lateral vibration shocks with magnitudes greater than 50 Gs. Our discussion will look into 6 BHA dynamic motions: axial, lateral, torsional, BHA whirl, stick slip, and eccentric. These can exist separately or can be present together. Proper identification of the vibration mode is essential in order to recommend the correct cure. Axial shocks arise from movement of the drill string along the axis of the drill string. In the most severe form, it is sometimes referred to as bit hopping or bit bounce. However, in most cases, there is not enough force to allow the drill string to come off bottom and bounce. Instead, shocks are transmitted up the drill string, which harmonically increases and decreases the weight on bit. The consequences of axial shocks could be broken bit teeth, damaged downhole tools, and slowed ROP. Lateral shocks result from lateral motion of the BHA from one side of the wellbore to the other causing it to bang randomly against the sides of the borehole wall. Torsional shocks result from the momentary slowing down or stopping of the drill string. This occurs when the bit digs into the formation deeply enough to slow it down relative to the drill string, or when a stabilizer digs into the formation. This causes a winding effect in the drill string, which can fatigue the drill string and BHA. BHA whirl is very complex and exists as a result of understabilized drill string and forces acting upon the BHA, such as rotating close to a resonant RPM or enlarged borehole. Whirl occurs most frequently, but is not limited to, near vertical wells. It occurs when there is enough sideways or lateral movement in the BHA for it to contact the wellbore wall. In the video, we see a rolling shock test where BHA components mounted horizontally are anchored at each end and rotated. In the center, a 10.5-inch steel casing ring is attached to simulate the borehole. There are three main types of BHA whirl: forward, backward, and chaotic whirl. Forward whirl is when the BHA rubs the formation along the same part of the collar as the drill string rotates. If the formation is abrasive, excessive wear will occur along the part of the collar that rubs the formation. This wear is seen as flat spots on one side of the collar, or as a single worn blade of a stabilizer. In forward whirl, the BHA still rotates in the same direction as the drill string. Forward whirl can destroy bits and BHAs. Backward whirl is very similar to forward whirl, except friction between the formation and BHA is greater. This increased friction results in increased torque on the BHA, which causes the BHA to rotate in the opposite direction of the rotation of the drill string. If whirling is backwards, then the collar connections can flex and fatigue at a very fast rate, resulting in accelerated fatigue cracking, washouts, and possible twist-offs. In chaotic whirl, there is no preferential side of the collars or BHA contacting the formation. The torque will be above average along with the lateral vibrations and shocks. Chaotic whirl can occur when changing rotary RPM to try and address forward or backward whirl. Bit whirl is associated with PTC bits because of their aggressive side-cutting action in harder rocks and near vertical holes. It is caused by non-symmetric cutting action of a real formation that displaces the bit from its center of rotation and then allows the bit to move. Verification of shock and vibration can often be obtained by examining the bit after a trip. When dealing with BHA whirl, it is sometimes necessary to stop drilling completely to cure it, depending on the severity of the shocks and difficulties with drilling. Stick slip is the non-uniform rotation of the drill string. This is the rotational slowing down and acceleration of the BHA. In extreme cases, the BHA can stop or even reverse its direction. During drilling, friction builds up, causing the BHA to momentarily turn at a slower rate than the surface pipe, or even stop. As this happens, the string stores the energy imparted by the rotary or top drive in the drill string. As this energy builds up, the friction-slowing BHA rotation will be overcome. When the stored energy is released, the BHA has to catch up to the rotary table. This results in a rapid increase in BHA rotation. Since it has now gone beyond the number of rotations the rotary has made, it will now spin backwards for a short period to become in step with the rotary RPM. When this happens, an inadvertent unscrewing of a connection can occur. Our review of shock and vibration effects in drilling is a good starting point for your understanding of the issues raised by these phenomena in the drilling environment. Schlumberger wants you to develop your knowledge of these issues, how to detect them, and how to mitigate them. These different types of shock occur simultaneously, creating serious drilling problems, which often require drilling to stop and then restart. Careful planning, execution, and post-job analysis will often reduce the risk of these shock and vibration hazards. We hope this presentation will assist you in this endeavor. Thanks for your attention.
The drill string is subject to 4 distinct types of shock and vibration: axial, torsional, lateral, and eccentered motion. Each has a unique effect on performance and tool life. Axial vibration, often referred to as bit bounce, is a vertical hammering motion along the drill string axis. This repetitive loading reduces drilling efficiency and accelerates bit wear. Torsional vibration includes stick slip, where the bit alternates between sticking against the rock and suddenly releasing with a torque spike. These sharp accelerations can severely damage both the bit and drive system. Lateral vibration, or whirl, occurs when the drill string moves side to side against the borehole wall. Forward whirl keeps the bit slightly off center, while backward whirl slams it violently into the formation. Both can quickly damage stabilizers, reamers, and the borehole itself. The fourth type, eccentered motion, happens when the drill string rotates around an off-center axis in a motion called BHA whirl. This creates uneven loading across the BHA, generating erratic forces and wear patterns. It is particularly destructive because it combines elements of lateral and torsional vibration. To manage shocks and vibrations, we must first measure them accurately. Data gathering takes place through 2 complementary systems: surface sensors and downhole sensors. Surface sensors are mounted on rig equipment and measure variables such as torque, rotary speed, hook load, and standpipe pressure. These values provide indirect evidence of vibration by showing irregularities or fluctuations that correspond to downhole motion. The advantage is that surface data is continuous and cost-effective. Downhole sensors, by contrast, provide direct measurement at the point of interest. Tools placed in the BHA record axial acceleration, torsional vibration, and lateral forces. This data is far more accurate, but it comes at a higher cost and may only be available when tools are retrieved. By combining both data sets, we gain the most complete understanding of shock behavior. With data in hand, we can now step back to a broader perspective and consider how downhole drilling mechanics fit into the bigger operational context. To fully understand shocks and vibrations, we must place them in the wider framework of drilling mechanics. Downhole behavior is never isolated. It is the result of interactions between bit design, formation properties, well trajectory, and operational parameters. For instance, a change in rotary speed may not only affect torsional vibration, but also alter bit aggressiveness, which in turn influences axial loading. Similarly, the choice of stabilizer placement modifies lateral forces along the string. Each adjustment we make at surface cascades into multiple effects downhole. The next video shows a downhole drilling mechanics service.
This service integrates data from the downhole sub with data from surface to provide actionable information at the rig site. The real-time drilling dashboard helps you optimize drilling parameters and intervene early, reducing the probability and severity of undesirable events. When the bottom hole assembly crosses a formation boundary, whirl, bit bounce, or stick slip motions can occur. In this case, backwards whirl is occurring and is immediately detected by the service. A real-time summary of the motion appears on the rig site display, alongside a recommendation to stop and then restart at a lower surface RPM to mitigate the risk. Annular and internal pressure and temperature measurements help to identify and mitigate poor hole cleaning and maintain wellbore stability. High-resolution bending moment provides information about the curvature of the borehole, enabling delivery of a smooth wellbore. Downhole weight on bit and torque measurements are used to monitor the bit-rock interaction and improve ROP. They also provide early indication of changes in borehole friction to avoid stuck pipe. Data from the OptiDrill service is transmitted to surface for use by the rig site team and interpretation by remote experts. The experts collaborate with the drilling team to reduce risk, improve drilling performance, and manage borehole quality. OptiDrill Real-Time Drilling Intelligence Service.
Let's now review the key learning objectives for this sub-module and tie them back to the material we've covered. We began by asking why shocks must be monitored. We saw that shocks waste energy, reduce drilling efficiency, and accelerate wear on drill string components. Next, we examined how shock damage accumulates, shortening tool life even when no outright failure is visible, and why inspection must account for shock history. We then looked at how good drilling practice directly translates into savings by reducing trips, extending bit runs, and lowering maintenance costs. Following that, we identified the major contributors to rough drilling: formation properties, borehole condition, well path geometry, and hole cleaning. Each was shown to play a role in vibration. From there, we studied drill string dynamic motions, axial, torsional, and lateral, and considered how they are detected through surface and downhole sensors. Finally, we placed all of this within the broader drilling mechanics context, emphasizing that vibration control must be integrated into the overall optimization process. Together, these objectives have given us a structured understanding of shock and vibration management in drilling. With this review complete, we are now ready to conclude the session. That concludes submodule 1 of 4 on drilling mechanics, shocks, and vibrations. Thank you for your attention and engagement throughout this session. Please proceed to the short quiz that follows to test your understanding of the material. Once again, thank you, and I look forward to continuing with the next submodule.